Thank you very much. So I think I'll build on a lot of the ideas presented from a slightly different perspective. I am leading the application development project for ECP, the Exascale computing project, which Doug Cothe spoke about earlier, for those of you who were here. Just a reminder about the project itself to give you sort of the big picture. You can think of it as the Department of Energy's push to get from current leadership class systems, which are 10 to 20 petaflops in the United States, to some definition of an exascale, which I'll get a chance to talk about in a little more depth as we move forward. And there are sort of two components to it, and it's important to separate them because it kind of informs part of our strategy. The ECI is composed of the hardware procurement, and that includes 2 exascale systems, the first one probably around 2021. And then there is the Exascale computing project, which is a lot of the underlying research, both the hardware R&D, collaborating via path forward with industry, as well as the development of solvers, middleware, and system software. And then the part that I'm most concerned with, which is the push to have mission-critical Department of Energy applications use these next-generation systems to do new science and to use them, by some definition, efficiently. So in the application portfolio, we have 25 applications that we're trying to, at the same time that these machines are being developed, the technology is being developed and matured, we're worried about how getting ahead of the curve and starting to think now about how we're going to run these on the next generation machines. And the breakdown of applications, Doug spoke in some depth about a few different areas, but just to give a sense, there are 4 to 5 applications in each of these areas. These are sort of nominal groupings. So in energy, for example, we have fusion, whole device modeling for ITER. We have fission, small modular reactors. We have combustion. Doug talked a little about the Pele code. In chemistry and materials, we have heterogeneous catalysis, quantum Monte Carlo, earth and space science, computational cosmology, climate, astrophysics. We actually have a separate bin, which doesn't really fit the thematic element of the others, but which includes one thing Doug spoke about, which is the Cancer Moonshot project, but other projects that are less traditional HPC and more focused on data-centric approaches, I'd say loosely, and they fall under this bin. We have security applications, which are of a slightly different flavor. And then we have co-design, and this is actually very important. The co-design efforts represent an attempt to leverage a lot of common computational patterns, which you might be familiar with, are known as motifs, and there are nominally 13 motifs that were codified in a very popular Berkeley report some years back. And the idea is that this co-design is really a collaboration between the applications and the library developers to develop technologies that many applications would leverage. And Doug gave a very good example of adaptive mesh refinement, particularly for shock capturing hydrodynamics. So there was a co-design project, AMREX, which endeavors to look at that problem in a cross-cutting way across applications for Exascale. Okay, so I'm going to talk from a slightly different perspective than Doug. First, I'll reiterate this slide because I think it's important to know where we are. It gives you a perspective of why we're going where we are. So the things right here are kind of being decommissioned right now. These are kind of the 10 to 20 petaflop systems. These are Power PCs, the Argonne Blue Gene machine. Titan is, of course, the Opterons with the NVIDIA accelerators. It got a boost recently, so it kind of really exists in both of these categories. And then another Blue Gene machine, Sequoia at Livermore. These are kind of on their way out, right? These are different platforms, not really much more performance, actually. So Knight's Landing, so these are heterogeneous Xeon KNL processors on Cori at Lawrence Berkeley. Argonne bought a Phi cluster, which is around 7 petaflops. And then there is a Xeon KNL hybrid machine, Trinity. So these are sort of all nominally the 10 to 20 petaflop systems that we think of as our baseline as we enter the project and we ask, where can we go from here for the mission-critical applications that we've defined. And so what we're seeing right now, which Doug spoke a little about, is Summit, which is the mixture between the Power 9 and the Volta accelerators, and same thing for Sierra at Livermore. And we have early tests on the Summit architecture. We actually have some, the whole other talk, I think, would be pretty encouraging performance numbers, actually. Around 2020, NERSC and LANL and Sandia will get pre-exascale machines. But here's what we're really targeting, okay? Now, these dates until contracts are signed are not totally firm yet, but we're targeting first just ahead the A21 machine at Argonne, and then at Oak Ridge, the Frontier machine. And then part of our plan will also include El Capitan at Livermore. So the really critical big picture issue, I always regret when I make an animation sequence, so let me finish that. So the big picture issue is we want to ask ourselves now, when this procurement takes place and when the hardware hits the floor at Argonne, all of the things that we depend on doing for the DOE mission, are we going to have to wait a year or two to be able to run them? Are we going to get anything like the performance boost proportional to what the machine advertises in some theoretical sense? So the key thing is we have to start thinking about this now, and that's what we've been doing. And I'll tell you how, and I'll tell you our concerns and observations. So preparing applications for Exascale. I'll talk about what the challenges are, and then I'll talk about what we're doing about it. It's sort of very common in this field to just say how difficult everything is. It's how awful. You have this long list of impossible things, and then you sort of end the talk. So I'm hoping not to do that, but that's where I'm going to start. Okay, so not really. I want to make some observations, and I'm speaking very much from an application perspective, not from a hardware or system software perspective. So you have an application that you run to compute something that is critical for your industry or for a mission, and what are you confronting? What are you going to do about it? Okay, so here is the slide of things that I think is the first concern, and you just have to use this as a starting point. I think it echoes a lot of things that you said, but the big concern is if we focus on flops at Exascale, they'll just be harder to get to, and we won't have anything like the performance improvements you'd expect from some peak theoretical number that's advertised. And I just made a list off the top of my head at why the machine might be too specialized to be able to efficiently access its potential performance. And here are all the things that I came up with very quickly. The obvious one, which you can't really get around, is it's assuming extreme 100 million way parallelism is already inherent in your algorithm and in your application. So that's already a tough bar to climb over for a lot of applications, but there's not a lot you can do about that. The next one, which we heard a lot about in Stephen's talk previously, is just the same old issue, which you hope at best, you hope it doesn't get worse, but it's that all of our near peak performance on algorithms has been by masking the latency to main memory by having high computational intensity. So you can do a lot of data reuse, many floating point operations per load, but that is a relatively restricted workload. Of course, it's part of doing dense linear algebra, might be part of doing the n-body problem. I mean, there are definitely algorithms that fit that mold, but of course, sparse linear algebra doesn't at all. The worst thing in the world would be random lookups for like a Monte Carlo code, graph-based algorithms, all sorts of things. I mean, we just saw the curve and floating point intensity, or the spectrum of applications. So the question is, will this get worse? And of course, if you're limited by your ability to move data into memory, and then you get a machine with 50 times the floating point performance, but it's no better or worse in that regard, you're not going to meet the goals of your project. You're not going to be able to do the science that you want to do. So that is something that has always been a concern, and it's not new now. Concern that's become bigger more recently is just how much RAM you have per flop. And the reason is simple. I mean, we're looking now in the sort of 5, I don't even think we'll see 10%. And the reason is that in order to find enough work to justify that level of parallelism, you need a big footprint of data. That's how most HPC works. And so if that footprint is small, then it's hard to extract, especially at coarse enough granularity, enough parallelism. So we're moving in this regime that we have to worry about. Is it assuming weak scaling? And this is a big issue that a lot of vendors don't think about that we've pushed on for the past few years, and that is, what if you want to strong scale a problem? Okay, so what if you want, now obviously there's a limit to that, you can't strong scale forever, but if you have a fixed size problem, which describes, frankly, a non-trivial portion of our application workload, and you smear it out finer and finer across processors, what's that cutoff where you hit your strong scaling limit because communication dominates local work? And the typical way of measuring that is, like with the LIMPAC benchmark, you have something called n sub 1/2, which is how big does the problem have to be before you approach some asymptotic performance limit on the machine. Well, if that number is getting bigger, if you have very fat nodes, very complex nodes that you have to feed a lot of data to in order to approach their theoretical limit, then suddenly that number, that threshold where you can strong scale, actually goes up. And exascale might look worse than petascale for that class of problems. And this is particularly important for our CFD codes, because we have very particular problems that we want to solve, and they need to be spread pretty thin, and they need to run fast, because CFD is intolerably slow if you're doing anything like LES or DNS. Okay, so it's important not to think of just the node itself, but the entire system and what that implies. So we heard a lot about optimized data movement. What might it look like to the programmer? I mean, the things that the hardware person has to confront are very different, but for a programmer, it could just mean, there's reduced clock speeds. There could be some kind of throttling that takes place if you're not efficiently programming a system and you're using far too much power by moving data distances that you don't have to. And then, of course, there are the other issues that have been around for a while, like wider vector units, algorithms that can take advantage of SIMD instructions is a relatively narrow subset. And then there are other issues like specialized instruction mixes, sufficient instruction level parallelism, and then, of course, we have to worry about Amdahl headroom for accelerator type systems, okay, where if you have, you're always going to have that bottleneck if you're going to be running an accelerator in combination with some latency optimized core. So there are a lot of things that you worry about up front. And I'm not saying that there aren't things you can do about a lot of them, but it's important to lay them out. Okay, so let me talk about what the approach is in the project to accomplishing our goals. The first thing is that each project has to define a mission-critical science and engineering problem. And it has to be a problem that cannot be done on a current leadership class platform. Okay, that's key. So it's not going to be a benchmark. It's not going to be crank up the resolution of homogeneous isotropic turbulence in a box. It'll be something that you could argue is an important step forward. And that's important because without that, it's easy to have a machine that gives performance improvements for very isolated, idealized things. So we start with that, and we're actually on the hook. So we're on the hook to demonstrate, one, that when this exascale machine hits the floor, that we can run the problem. So that would be at first building it and executing some form of it at whatever performance within some specified amount of time, not a year later. Okay? And the second piece is that we have to define and achieve a figure of merit. And so the figure of merit is for each application, and then for the project as a whole, it's some kind of average. The details don't really matter, right? But if you think about it, that's kind of scary, right? I mean, you're promising at this point for a machine that is going to be fairly exotic, that you're going to achieve a certain amount of performance increase. And the figure of merit, could be speed up, it could be the size of the problem, you could have some way of accounting for new physics, it could be some combination of those things. So each of the 25 applications has a specific definition of how they should be measured in the future versus how their performance is measured now. So sort of a ratio of capabilities. All right, so that's important. Now, what are we confronting when we look at this suite of applications? So first, how are the applications programmed? And what changes will be needed to even just build and run the code on the exascale machine, and then to be able to make reasonably efficient use of the hardware? And the question is, are current programming models good enough? So there's a major investment in software in all of these codes, and in a lot of cases, they need to continuously be used to carry out calculations, whether it's in national security or in the analysis of certain energy systems, that they can't just be sort of thrown out and recoded from scratch. An enormous amount of effort into validation. So it's important first question is sort of what can we expect from the programming model side of things? And if you look at across the 25 applications, and I have numbers, but it's not really interesting to show at that granularity. So if you just look at the internode and the on-node programming models that are in each application, and you just bin them by sort of the number that use each of those technologies. So if you look at internode, of course, everybody's using MPI, but some people use it implicitly by using higher level libraries like solver libraries like PETC, Trilinos, or Hypera, or something else. You know, some it's coded explicitly by the application developer. And then on Node, if you look at OpenMP, there's a certain point, 5 or 10 years ago, when 60 or 75% of the applications went to an MPI plus X model, where for certain applications, OpenMP does better on Node than MPI does. It's not true in all cases. But that's kind of where and then, of course, CUDA kind of snuck in, and if you have an application where your performance is very concentrated in a small fraction of the code, it's kind of easy to go play those games and to program it in CUDA and test it on the accelerator. So we're kind of really, here's where we are, right? And here's where most everything is. And that represents a significant software investment. And there are lots of one-off, specific developments for different projects, but they're not in any way represented across the application suite. Okay, so all MPI, one form or another, in MPI, OpenMP are really ubiquitous, even setting aside the programming language, which I think Doug mentioned earlier is probably 40 to 50% Fortran. And there's also, and this is very important for thinking about what we're doing, there's heavy dependence of MPI built into middleware. Sometime 10 or 15 years ago, it became very popular in DOE for starting new projects to build them off of solver building blocks instead of rolling your own conjugate gradient solver or doing your own dense linear algebra. So that's kind of where we stand. Okay, so the first question is, will we need new programming models? What's our view on that? So obviously there is a huge software cost and even bigger risk to adopting a new programming model. It's very difficult to predict and to gain traction with something that's completely different, although there are dozens of efforts all over the research community. But we have to recognize that the abstract machine model that underlies both MPI and OpenMP has shortcomings. And the two most obvious ones, and you could give a whole talk on these shortcomings, but the most obvious one, which is being addressed, but is locality in OpenMP, right? So the assumption that where you place the data doesn't matter, and that you just have tasks, and you just divide the tasks among OpenMP threads isn't going to work at all in a case where you have memory affinity. Even now, on machines, NUMA machines, it performs very poorly compared to ways that we have of expressing on-node locality. So this is obviously something that's just a big problem, but let's get bigger. And then, of course, for MPI, the one thing we've heard for years is the idea of synchronizing across an exascale machine. And you don't have to program MPI in a bulk synchronous mode, but that is the most natural way to do it. And that is what the programming model invites, is going to be prohibitively expensive. So there's a lot of work in reduced communication, asynchronous algorithms for doing things like conjugate gradient, for even doing dense linear algebra. So instead of everybody doing a dot product and synchronizing at the dot product, you enter your piece into the dot product, and then you continue to do your next orthogonalization for doing conjugate gradient. I mean, so Jim Demmel has kind of cornered the market on this kind of research. And it's really fascinating, and it's just a different way to think about doing it. You really put front and center, what can we do to avoid waiting for everybody else, right? So I think that the way that we were able to pretty seamlessly move from one generation to the other by just thinking of a machine as a collection of nodes with a virtual rank that could communicate with other nodes is obviously gone. And so, what will the new, this is not obviously appropriate for the new abstract machine model. The good news is that we have participation in these standards committees, and they're changing very fast. So they might look very different. I mean, we have 2 MPI projects that are being funded under ECP and 1 OpenMP project. And these issues are being addressed. So that can give comfort that you can have familiarity in your programming models and not be stuck with a lot of these issues. And I just mentioned 2 of them here. But there are still concerns. A lot of people feel like we could do much better for the community if we could express our parallelism at a higher level of abstraction. Okay, if we can define tasks and graphs that describe dependencies of tasks and give a runtime system, hand it over to a runtime system and let them optimize it on hardware. Okay, of course it sounds great and it makes a lot more sense, and people think ultimately, whether it's now or 10 years from now, ultimately things will have to be done that way, to not lock yourself into a very specialized system and to be able to manage the complexity of your software. Okay, so this is very important. And there's a lot of concern in the project about not targeting one platform and getting very good performance on it, and then having a software nightmare. Okay, so this ties into performance portability. And then the question is, how do accelerators, which are, I would say, inevitable in what I see, how do they play into this, and what impact do they have? So I'll make a comment about that. So given what we've heard about performance per watt, specialized accelerators, together with maybe more traditional processors, seem fairly inevitable. I can't totally say what's going to happen, but it's sort of on the pre-exascale systems they're there, and there's a very good reason why they are. And it seems inevitable that they'll be part of at least some, if not all, exascale solutions. And accelerators are even a heavier lift for something like OpenMP, although there's research in having OpenMP directives for doing accelerator offloads. Also, there's the question of using MPI to have accelerators talk directly to each other and not going back through the host, which becomes a bottleneck, right? So even though we might have low software cost by retaining our familiar programming models, it might give us horrible performance. Okay, so that's our other big concern, right? How far are we willing to go to have a familiar tool chain, a familiar programming model, if in the end we have to dig in and do very specific optimization to get reasonable performance? Okay, so what we've seen is who's really on the cutting edge among our suite of projects. And who's on the cutting edge are those projects who have a very high concentration of their computational performance in a very small amount of code. And of course, unfortunately, not everybody is like that, but maybe a third of the applications can point to one kernel where 95% of the floating point operations take place. And they can have different versions of that kernel for different systems. And they're not even so concerned about having one way to program it. They'll gladly if-def 6 different versions of it for 6 different pieces of hardware. It makes it a much easier problem. The people who have a much more difficult situation are kind of the opposite extreme. And then there are lots of teams in the middle. Okay. So you might have noticed, and I think this is one thing that's very confusing to the PIs in the project, that the sort of power void that was left by the apparent sudden weakness of MPI and OpenMP has created a rush of new developments of programming models. So everybody, 50 projects of people who have ways of expressing parallelism in an application that seem better in theory than doing it the old way. And I would say this is natural and not a very bad thing necessarily for now. It's sort of how standards are always developed. People try lots of things, we see what works, and a posteriori, we all get together and we say, let's try to build one common standard that kind of fits what everybody's doing. But right now it's a bit of a mess, right? So hopefully this will coalesce at some point. And the plans certainly include MPI and OpenMP. I think that's pretty clear. But for our projects on Node, many projects are experimenting with new approaches that aim at the kind of device portability I spoke about. So we see things like Oka, which actually was here at Rice originally. So Tim Warburton, I think, went to Virginia Tech. But it was an interesting and promising project. Again, you write in a higher level language, and the code for devices is generated automatically based off of how you describe it in this high level language. Cocos and Raja, Sandia and Livermore, OpenACC, OpenCL, Swift. So if I just go through the projects and look at what people are working on, everyone's kind of experimenting with something. And they're also willing to have as backup MPI plus X, where X is either OpenMP or OpenACC, or if the two merge, maybe that's not different, and or maybe CUDA, okay? In internode, some projects are even looking beyond MPI plus X at new non-traditional approaches. So we heard a little about Legion. I'm not quite sure what I'm allowed to say, but I'll just say at least a couple of projects, one of them is the combustion project actually, are hanging their hat on Legion to do the full thing, okay, not just for on-node parallelism. Legion is a task-based programming model out of Stanford. Research project, but with a lot of traction, a lot of a lot of success to this point. Few use UPC++. It's always been good for certain types of communication, but not as broadly useful as MPI. But a number of applications are using it, and 2 or 3 are using global arrays also. So there's a lot of experimenting going on. At the same time, people are ready to have as their backup plan what they're familiar with, because it's very uncharted territory. Okay, another thing that's very important for what we're doing is when you organize the project to ask, all these codes are dependent on application level middleware like PetSiege for Linux and Hypera, or we heard about Chombo or Meshlib or whatever. You know, these things have to be able to run on the machine before the codes run on the machine. And that's why it's always been, there've always been a sort of grumpy group of old HPC people who refused to have any library dependencies at all. And they're very proud of it. It didn't matter how much they had to write themselves. And this is the reason, right? It's because they've always lived on the cutting edge of HPC, and they don't want to depend on something else to be able to be the first one on the machine. And you know you're going to get a C compiler or hopefully a Fortran compiler. Beyond that, you don't really know what you're going to get, right? So as a project, we are funding research in these areas, and we have to be very mindful of which applications need them and make sure that they're ready by the time the applications use them. It implies also working very closely with applications. We heard about Chombo being directly funded as part of our co-design project. So this is a major focus of the project as well. Okay, so a lot of other thinking is going on prior to people knowing exactly what this exascale system will look like, though the picture is becoming clearer, okay? And there's a lot of rethinking algorithms and even rethinking the types of physics that we might want to do based off of what the systems look like. And that's kind of the pushback. So I just made a list of different categories that apply in our project. The first one, of course, is reduced communication and data movement. So this would involve, for example, duplicating data structures to limit the number of times you have to move them off node. It would include asynchronous solvers, and there's work going on for sparse linear algebra. There's work going on for dense linear algebra in that area. Another is much greater locality awareness. So the idea that you have a node and tasks won't work at all. So people are thinking about how they're going to expose locality and, of course, what the programming will look like to allow them to do that. Another is the much higher cost of global synchronization. We talked about that. So we're going to favor asynchrony where possible with the physics. This issue came up, and that is a question that's very hard for HPC people to answer, which is obviously there's performance value to doing mixed precision, or to doing lower precision floating point, where you can get away with it. It's very hard for people to be confident where they can get away with it. It's just not a question that people can easily answer. People write papers about, you know, their thoughts on the matter, but they don't always sort of get to the answer. So it's surprisingly difficult in a lot of areas. People have sort of done the highest precision that they had available to them and didn't necessarily think about it deeply for many years. And then, of course, the fault resilience kind of became, fortunately, the domain of the people building the system more than the application people after a certain point. Okay, so let me say a few things beyond implementations, and then I'll wrap up. There's something else going on at the application level, and you might like it or you might not. You know, it might really bother you. It doesn't bother me, but it's, you know, I could see it being a little annoying. The realities of the hardware, so as you learn in working with vendors about what's going to happen that you can do nothing about, you know, there's some things you can push back on. There's some things you're not going to do anything about. And they can force you to think, how am I going to code the algorithm? When I say algorithm, maybe the model. How am I going to represent in a programming language the model that I would like to simulate? You can also ask other questions. And this is happening across the project as well. It's one of the more interesting things that I didn't necessarily expect. And that is, you can ask if you shouldn't embrace a totally different class of models to do the same physics, but with a very different perspective, just because they look better on an exascale type platform. So, for example, Monte Carlo approach versus a deterministic approach. So estimating a multidimensional integral versus solving a partial differential equation, for example, for Boltzmann transport. Okay, you're solving the same thing. They look totally different to the computer regardless of how you implement them. It's not just a programming issue. A lot of table lookups, so particularly we're killed by random table lookups. And we just heard about gups. So we have the gups of, the application world, except it's not writing, it's all reading. And it's the worst thing you could do on a computer. It turns out that as we get more and more flops, we can recompute, for example, from very fundamental principles, the neutron cross-section values of nuclear materials, rather than have them pre-computed and look them up in a table every time there's an interaction between a neutron and a material. Okay, the things that would have seemed absolutely insane 15 years ago, not only do they look reasonable now, but in a lot of cases they're just better. Okay, so it's not just how do I code this thing, it's how do I sort of think about the problem. It's also when you're thinking about what might you do with an exascale machine, and you have a list of 5 things, you might pick that one and that one, all else equal. I'm not saying do something irrelevant, but you might pick the thing that looks like it has the most hope. At least that's where we are. Moving to higher, so Doug talked a little bit about this. I mean, for smooth, sort of incompressible flows, I like higher order methods anyhow for CFD, but that's been a big push in the project. We have the SEED project, the Center for, I can't remember now, exascale discretizations. I forgot one of the E's. But using more accurate methods where it's appropriate and being able to back off on grid resolution is a very nice bargain to make on an exascale machine because you have much higher computational intensity and you get away with a coarser grid. So we have a CFD code called NEC 5000, which is based off of higher order finite element method, which is known as the spectral element method, which uses this, and it's becoming adopted much more widely across the project where possible. And another one, so we've seen all sorts of things. Like normally if you want to statistically describe maybe a neutron population or a flow that is stochastic, you integrate it until it reaches equilibrium, then you do time averaging. Well, if you can't strong scale, the time averaging takes forever, right? And so you might ask yourself at a certain point, when is it better, instead of doing ergodic time averaging to get equilibrium statistics, why don't you just start n copies of the same thing, pay the cost of the transient, but then you don't have to worry one time per copy, but then you don't have to worry about the incredibly slow equilibration time. Oops, looks like my talk's there. All right, so let me just say a couple words in conclusion, and then I'll sit down. I'll mention the code design with the hardware vendors is critical to this. And we're involved in this now, and it's non-negotiable. So last point, I'll just say in summary, there is a major challenge for mission-critical HPC applications to get proportional performance moving toward exascale. If you're not limited by a resource then that isn't flops, then you run the risk of just not being able to get any speed up at all, like we heard about in Stephen's talk. So from an application perspective, there's a very high risk in being passive. And so we're engaging now with HPC vendors. I recommend being aware of emerging technologies, particularly new ideas and programming models, and at least being a fast follower in that area. And to consider driving new science and engineering opportunities by certain realities of exascale systems, not necessarily simply by what you've always done. Okay, that's all. Thanks.